So let's jump into it. We've already seen that this graph has two parameters, y equals mx plus b. The parameters here are the m and the b. And a lot of our algebraic work is going to be on finding the values of m and b. How do we determine the y-intercept? If we already have our line in y equals mx plus b form, we can just recognize it. Whereas on the graph, if we're looking at the place where x is equal to 0. On the other hand, Slope, you may remember, is defined as the change in the output, or the change in the y, divided by the change in the input. Notice that this is a ratio. This is a ratio of two things. We use slope all the time when we're driving in a car. You may not think about it, but when you look at the speedometer, you're actually looking at something like 55 miles per hour. That's 55 miles per 1 hour. So this is telling you the change in your distance divided by the change in your time. And so this is an example of slope. Now the slope is probably not always the same when you're driving a car because you stop and you accelerate, etc. But if you're driving on the highway, then this would approximately be the same. And so speed of a car can be an example of slope, and it's important to remember this is a rate. Slope is also known as rate of change, and this gives us insight into how to recognize a linear relationship is appropriate. You could ask, if I have 10 times change in the input, will I have 10 times change in the output? In other words, these relationships scale proportionally. An example of something that does have an approximately linear relationship, you can look at driving on the highway, because on a highway you're driving at almost the same speed all the time. If you're driving on the highway and you look at how much distance you've covered in 10 minutes and you compare it to how much distance you've covered in an hour, you would expect that the distance you could travel in 1 hour would be about 6 times the distance that you could travel in 10 minutes. Because 1 hour is 6 10-minute blocks. Also important to recognize when a nonlinear relationship exists and how we know that. The example that I'm going to give now is due to Nassim Taleb, who is one of my favorite thinkers. I'd highly encourage you to seek out his work. Nassim Taleb discusses the example of a car crash. Imagine that I am crashing my car into the wall. And let's suppose that I am tracking the damage as a function of velocity and number of crashes. So if I crash 50 times at 2 miles per hour, in all honesty, the damage to the car will probably be pretty minor. This is basically the idea behind bumper cars, that you can have a lot of small crashes that don't harm you that much. But unfortunately, damage doesn't scale linearly. If I do one crash at 100 miles an hour, then unfortunately, the consequences won't be good. I can look at some more examples of whether or not something is linear. These are going to come from basic geometry. Let's compare the perimeter of a square and the perimeter of a square as it depends on its side length, compared to the area of a square as it depends on side length. So if I look at the perimeter of a square, when the side length is 1, the perimeter sum of all the side lengths will be 4. And when the side length of each side is 2, the perimeter will be 2 plus 2 plus 2 plus 2, which is 8. So when the change in the input doubled from 1 to 2, the change in the output also doubled from 4 to 8. That's a linear relationship. If we do the same calculation for area, the area is the product of the side lengths. When the side length is 1, the area will be 1 times 1, which is 1. When the side length is 2, the area will be 2 times 2, which is 4. That's a nonlinear relationship. The area didn't double. From 1 to 4, the area, a non-proportional response. So recognizing whether or not a relationship is likely to be linear is an important thing, because that tells us what type of function we should use to model it. If this is all new to you, just be patient. You'll improve with practice and as you think about things carefully. But this gives us the basic ideas of when linear functions are used and how to recognize their basic form, both in mathematics, in their symbolic form, and in the real world by thinking about the underlying process that describes the function.